Welcome to this explainer. Okay, today we are going to tackle a classic physics puzzle, one that honestly trips up so many students. We're talking about what happens to the acceleration of a ball right after you throw it straight up into the air.
So let's just dive right into the big question. If a ball is moving upward, shouldn't its acceleration also point upward? I mean, it seems super logical, right? If something's going up, the push has to be up. It's a really common gut feeling. But, well, as we're about to see, physics has a little surprise for us.
All right, first up, let's talk about that puzzle. Why does our intuition kind of lead us astray here?
And look, let's be super clear. This is a totally normal way to think about it. It just feels right that if something's going up, there has to be this upward force or acceleration pushing it the whole time. But here's the key in physics. We have to draw a line between where an object is going and what is actually changing its motion.
So, to get to the real answer, we've got to set our intuition aside for a second and grab onto a fundamental rule of motion. Think of this as the golden rule for cracking any problem just like this one.
Okay, let's start with the basics. What even is acceleration? It's not just about getting faster. Acceleration is the rate of change of an object's velocity. And remember, velocity is both its speed and its direction. So the real question becomes, what makes that velocity change in the first place? And boom, here's the key, straight from Newton's second law. An object's acceleration is caused by the total or net force acting on it. This is huge. It means the direction of acceleration is always the same as the direction of the net force. They're like two sides of the same coin. If you find one, you've found the other. And this famous little equation, F net equals ma, that's our go-to tool. See, to find the acceleration, A, we don't even look at which way the ball is moving. Nope. Instead, our job is to play detective and find all the forces acting on the ball. That'll give us the net force, F net.
Okay, theory's great, but let's put this rule into action. Imagine our ball. It's just left your hand, and it's flying up through the air. What's going on?
This right here, this is the most critical question we have to answer. And just a quick reminder, for AP Physics 1, we pretty much always get to ignore air resistance, which makes things easier. So keeping that in mind, what's the only force acting on that ball once it's in freefall? The answer? There's just one. That's it. The only major force acting on that ball through its entire flight, on the way up, at the very peak, and on the way back down, is the force of gravity. And gravity only ever does one thing, it pulls straight down, always.
All right, let's bust some common myths here, things that might pop up and try to trick you. The force from your hand? No, that's gone. The hand isn't touching it anymore. What about an upward force of motion? That's not even a real force. Motion is what happens because of forces. And momentum? Momentum isn't a force acting on the ball, it's a property the ball has.
Okay, this is where it all clicks into place. If the only force is gravity, and gravity is always pulling down, well, what does that tell us about the acceleration? Let's follow the ball on its complete trip. So on the way up, the ball's velocity is obviously pointing up, but the net force, gravity, is pulling down. And since force and acceleration are locked together, that means the acceleration is also pointing down. And think about it. What happens when you have an upward velocity and a downward acceleration? You slow down, which is, exactly what the ball does.
Now for that magic moment at the very top of the arc. For a split second, the ball hangs there. It stops moving. But did gravity suddenly switch off? No way. The force of gravity is still pulling down, which means the acceleration is still pointing down, even when the ball isn't moving.
Yep, at that one instant, its velocity is zero. But the acceleration is absolutely not zero. In fact, that downward acceleration is the very thing that's about to grab that zero velocity and start pulling it downward in the next moment. And now for the easy part, the trip down. The velocity is pointing down, and the acceleration is, you guessed it, still pointing down. And when velocity and acceleration are on the same team, pointing in the same direction, the object speeds up. That's why it gets faster and faster as it falls. So the big, crucial takeaway here is that through the entire flight, up, peak, and down, the acceleration is constant. It doesn't change. Near Earth, it's always about 9.8 meters per second squared, and we just use a negative sign to show it's pointing down. It is constant, constant, constant.
Okay, let's put this all together and build our new, correct understanding of the difference between velocity and acceleration.
This chart just lays it all out perfectly. Just look at that acceleration column on the right. Down, down, down. It never changes. Now look at the velocity column. It's all over the place. It points up, then it's zero, then it points down. See? It's that constant downward acceleration that's causing all those changes in velocity.
And that's the big aha moment. Velocity and acceleration do not have to point in the same direction. When they point in opposite directions, it just means the object is slowing down. It's just like when you hit the brakes in a car. Your velocity is forward, but your acceleration is backward. It's the exact same idea.
So to take this one step further, I'm going to leave you with a little puzzle. If we know that acceleration is the slope of a velocity versus time graph, and we just proved that the acceleration for this ball is a constant negative number, what would that graph have to look like? Give it some thought. Thanks for joining me for this explainer.